So in this lecture we will learn about the LFKN protocol. So the protocol is named after the inventors of the protocol, Lund, Fortnov, Karlov and Nissan. The question is about calculating the permanent of a matrix. So we will see how using this protocol one can compute the permanent of a matrix. But before we get to that, we will look at this problem more carefully and see how it is related to some core computational issues. So let us just start with a small problem. So let us look at the problem of matching. Okay. So here there are n people, n men let us say, and n women. And we have this edge between a pair of people if this particular person is interested in the other person. So I comma j is an edge if I and j are okay with being partners of each other. So a natural question would be, can we find a perfect matching? Okay, that means find an arrangement. So let us say M1 or MIWI. So pair people in such a way such that MIWI is an edge. Okay. For example, if we take this particular diagram where there are 3 people, 3 men and 3 women, and the following edges are present. Now the vertices, if we name them as M1, M2, M3, W1, W2 and W3, the only perfect matching in this particular graph is M3, W1, M2, W2 and M1, W3. This is the only perfect matching in this particular graph. We could also ask how many perfect matchings are there. Okay, so in this there is only one perfect matching, whereas given an arbitrary bipartite graph, finding the number of perfect matching might be difficult. That is known to be a sharp P complete problem. Okay. Which means it is a very difficult problem. So sharp P is a complexity class and computing the number of perfect matchings is a complete problem for that particular class. Let us look at the following question. Suppose there are no perfect matchings in this. How do we convince somebody that there is no perfect matchings? So the total number of perfect matchings, let us say if there were 200 men and 200 women, the number of perfect matchings could be as large as 200 factorial. Okay. So if we wanted to say that there are no perfect matching, we could list down all the possible matchings and argue that none of them are perfect matchings, but that is prohibitively expensive because 200 factorial is not a small number. Now, if there were no perfect matchings, is there a way to convince someone that look, there are no perfect matchings? One could do that via Koenig's lemma. So, Koenig's lemma gives an if and only if condition for existence of perfect matching. Okay. G contains a perfect matching if and only if every subset S of M has at least size S neighbors. Okay. So, it means if there are no perfect matchings, then there is a subset whose number of neighbors is less than the size of the subset. Okay. So, in order to show that there are no perfect matchings, one has to just identify a subset such that the number of neighbors is strictly less than the size of the subset. So, if you find a 70 sized set such that its neighbors is less than or equal to 69, then we know that look, these set of vertices cannot be matched at all, they cannot all be simultaneously matched. So, this does not mean that finding that set is easy, but it says that if there were no perfect matching, then of course, there is one set, there is at least one set such that its neighbors is strictly less than the size of that set. So, one can convince another person that there are no perfect matchings. Okay. So, if you assume that you are infinitely powerful in terms of computation, then you can convince anybody that a given graph does not have a perfect matching if it really did not have a perfect matching. You will do that by just figuring out which is the subset which does the job. Now, let us look at a related problem. So, here we wanted to match amongst two set of vertices, you had to match M to W. Suppose we had a problem of matching within the same set. In other words, suppose you have n vertices and let us say here two people are connected by an edge if they do not mind being friends of each other. Okay. So, if you have an edge, that means they are okay, they are compatible. Now, we want to find a way in which these people can be seated around a table such that everybody is next to their, nobody is sitting with somebody who is not their friend. So, find an amicable seating. An amicable seating would essentially mean that your neighbors on the round table are your friends. Okay. Can this be done? Again, if there were 200 people here, there are 200 factorial possibilities. You could try out all possibilities, but suppose there are no such possibilities, that is, there are no Hamiltonian cycles. So, this is a question of, is there a Hamiltonian cycle in G? If there is, one can of course convince somebody by actually displaying the cycle. If there are none, then we need to look at all these 200 factorial possibilities. Is there some way, some clever argument like we had via Koenig's lemma in case of perfect matching, that there cannot be any Hamiltonian cycle? Okay. So, this is an example of a problem that is in sharp P. So, how does one solve this problem? So, here in case of perfect matching, it was easy to see that we could convince that there are none, but if there are, let us say, 80 perfect matchings, how do we convince somebody that there are 80 perfect matchings? Okay. So, the number of perfect matchings is related to some quantity known as permanent of a matrix. It can be shown that the number of Hamiltonian cycle is also related to the permanent of a suitably constructed matrix. If the number of Hamiltonian cycles is 0, the permanent of an associated matrix will be 0. We have not yet defined what the permanent of a matrix is, and that is what we will do in the next slide. Okay, so we will first define what is the permanent of a matrix. The permanents are defined for square matrices. So, consider an n cross n matrix. Its determinant is written in the following way. So, determinant of M is summation over all permutations M I sigma I. And this is a rather cryptic notation. We will just do this for a 3 cross 3 matrix. So, this is into sign of sigma. So, determinant of a matrix is summation over all permutations sigma. So, sigma belonging to Sn Mi sigma I times sin sigma. So, let us first look at a 3 cross 3 matrix. A21, A22, A23, A31, A32, A33. The determinant of this matrix would be A11 into A22 into A33, that is the first term. And the second term would be again A11 and then A23 and A32. And this has a negative sign. The next term would start with minus A12, then a term from the second row, that is A21, and a term from the third row, A33. The next term again would be with the plus sign A12 and a term from the second row, A23, A31. Okay. So, the determinant can be written as summation over products. So, sum is over all permutations sigma and product going from I equals 1 to n for an n cross n matrix, and each term has n terms and each term is of the form A I and sigma I. So, here so I is going from 1 to 3, A1, A2 and A3, and the this is A23 into A32, this into the sign. There is a sign associated with each permutation, and that is the formula for the determinant. If you ignore the sign, whatever you get is called as a permanent. So, permanent of a matrix M is equal to summation over all permutations product I going from 1 to n A I sigma I, where sigma is any permutation on n length. So, we want to compute this particular quantity. Okay. Although determinant computation is very easy, you can do Gaussian elimination and compute the determinant, there are no easy algorithms known for computing the permanent. It is known that computing permanent is a sharp P complete problem. Just say that permanent is sharp P complete. Okay. This also means that if you can compute permanent, you can count the number of perfect matchings in a graph, you can count the number of Hamiltonian cycles in a graph, and so on. Okay. So, here in this lecture we will see protocol to compute the permanent of a matrix. There is some difference in this computation and the standard algorithm. In the sense, here we will think of this as an interaction between two people. Okay. So, when we say a protocol, what we have in mind is the following. We will make the following assumptions. Assume that the adversary, there is another, so think of this as a 2-player game, and you are one player and there is the second player, and the other, we will assume that the adversary or the other player is computationally unbounded. So, he can do any computations very quickly, but cannot be trusted. In the sense, the adversary might try to cheat you. He is capable of doing computations quickly, but he might not convey the answers to you faithfully. On the other hand, you are polynomially bounded. In other words, you can do only a polynomial amount of computations at a given time. Okay. Now, the objective is, we want to answer this question: can the adversary convince you that the permanent of a matrix M is equal to small m. Okay. So, there is a given matrix that is common for you and the adversary, and the adversary somehow quickly figures out what is the permanent, and now the adversary wants to convince you that it is indeed M. You could try and compute it yourselves, but that is going to be an exponential time computation. It is not clear how permanents can be computed quickly. So, now can the adversary convince you that the permanent is indeed small m? Okay. So, we will see that randomization helps in this particular task. Okay. So, we will begin with the following simpler problem. So, let us say that there are two matrices M1 and M2, okay, and the adversary has said that the permanent of M1 is small m1 and the permanent of M2, the matrix M2, is small m2. One of these answers is incorrect, or you suspect that it is incorrect. Okay. You are not sure, but you think that at least one of them is incorrect. Now, is there a way by which you can force the adversary to commit to the permanent of a single matrix whose value has to be incorrect with high probability? Okay. So, here you are in a situation where you think that one of these matrices is incorrect, one of these answers is incorrect, one of these permanents is an incorrect value. Can you somehow force the adversary to give a single matrix whose permanent is falsely stated? We will see that that can be done. Okay. So, what you will do is, once you got these M1 and M2, you will think of the following matrix, which let me call it as dx, where x is a variable. So, this is the matrix x times M1 plus 1 minus x times M2. We will assume that M1 and M2 are both n cross n matrices. Okay. So, this means take the matrix M1, multiply every term with x, you will get a matrix with a variable at each position, and you take the matrix M2, multiply it with 1 minus x, and this new matrix that you get, you call it as dx. Once you fix the value of x, you will get a single matrix, but for different values you have different matrices. Now, D is a matrix whose entries are linear polynomials. So, you can ask the adversary for the permanent of dx. So, that is the first thing that you would do, ask the adversary for permanent of d1 of dx. Now, the permanent of dx is not a number, but it is a polynomial of degree at most n. So, the permanent is a polynomial whose degree is at most n. Now, think about the following problem. If the adversary had stated the values of the permanent of M1 and M2 incorrectly, even if he stated one of them incorrectly, can he afford to give the correct value of the polynomial dx? If he gives the correct value of the polynomial dx, you can substitute x equals 1 and recover the correct value of the permanent of M1, and if you substitute x is equal to 0, you will get the correct value for the permanent of M2. Okay. So, substituting x equals 0 and 1 helps in recovering the permanent of M1 and M2. If the adversary has lied in the values of the permanent of M1 and M2, he has to lie in the permanent of D, because if he correctly states the permanent of D, then from that you can find that the adversary had lied. So, now if he states an incorrect polynomial, can we somehow figure out that he has lied? That is also easy. Suppose D was the actual polynomial and the adversary, if he has not given the correct polynomial, let us call it as D1x. So, this is supplied by the adversary. Note that dx is the actual one. Okay. So, dx and d1x can agree on at most n points. So, suppose small n was something like, let us say 1000, you choose capital N is equal to let us say 50,000 or 50 lakh, the probability that dx is equal to d1x is going to be less than or equal to 1000 by 50,000 or 50 lakh. Okay. So, if he has incorrectly stated the value of one of the permanents, we are forcing him to incorrectly state the permanent of the matrix dx for some random value x, and he can be successful in hiding his lie only with a very small negligible probability. Okay. So, we had the situation that the adversary had lied about one of the permanents, we force him to lying on the value of a single matrix capital D. Okay. So, now how can we use this fact to have a protocol for computing the permanent of an arbitrary matrix? So, let us just write down what we have achieved. Given the permanent of M1 and M2, we can force the adversary to give the permanent of a single matrix, let us say D. If the permanent of M1 and M2 were incorrectly stated, with very high probability the adversary will have to lie about the permanent of D. Okay. So, if we had a collection of matrices M1, M2, Mk, we can do this k times. We can first combine M1 and M2 in this particular manner, and that result you can combine with M3 and so on. So, even if we are given k matrices and if the adversary had lied in even one of those permanents, we can force him to give the permanent of a single matrix. If you are given m matrices and the adversary has given the permanent of each of those matrices, if he has lied in even one of them, we will catch the lie with high probability by forcing him to lie about the permanent of a single matrix. Okay. So, how do we use this to compute the permanent of a single matrix? So, let us say M is the matrix and the adversary has stated that its permanent is small m. Okay. Now, we ask the adversary for the permanent of n matrices which are of dimension n minus 1 cross n minus 1. Okay. Namely, we look at the minor matrices. So, if you have this matrix and if you expand along the first row corresponding to this particular entry, we will look at the matrix obtained by throwing out the first row and the jth column. Okay. So, there are n minus 1 such there are n such matrices. we ask for the permanent of all those matrices. So, these M matrices, if you call it as M1 to Mn, and if these values were A11, A12 and A1n, we can ask the adversary to give the permanent of all these matrices M1 to Mn. If he has correctly stated the values of M1 to Mn, he cannot really be lying about the value of M, because permanent of M is equal to A11 into permanent of M1 plus A12 into permanent of M2, so on up to A1n into permanent of Mn. If the permanent of M was incorrectly stated, then the adversary must give incorrect values for at least one of these matrices. If he has given the correct value for the permanent of these matrices, we can do this consistency check of multiplying each of the permanents with the appropriate Aij's and adding them up, and we can compute the true value of the permanent. So, if the true value of the permanent was incorrectly stated, it forces the adversary to lie about the correct values of the permanent of the submatrices. And so, now we are at this particular stage where instead of the permanent of a single n cross n matrix, the adversary has now given us the permanent of n minus 1 cross n minus 1 matrix, out of which at least one of them is going to be incorrect. If he had correctly stated the permanent of M, there is no problem. If he has incorrectly stated the permanent of M, then at least one of these smaller matrices, then the adversary must give an incorrect value for at least one of the smaller matrices. We can of course combine them and get a single n minus 1 matrix whose permanent is incorrectly stated. Okay. So, we can combine the n matrices to obtain a single matrix. Okay. But now the dimension is n minus 1 cross n minus 1. So, if the adversary has lied on a single matrix of size n cross n, we will force him to lie on a single matrix of size n minus 1 cross n minus 1, and this can recurs, and in the end he has to lie about the permanent of a 1 cross 1 matrix, but the permanence of a 1 cross 1 matrix we can anyway directly find out, and therefore the adversary's lie can always be caught with very high probability. We argued that if we choose our n to be large enough, higher than the degree of the polynomial, then we will get an error of small n, the degree, by capital N, where capital N is the size of the universe from which we chose our random number. So, small n by capital N is the probability of error if we were doing this once, but we had combined n matrices into a single matrix, and that would incur an error of n square by n. And then after combining n of these matrices, we again recurse for another n step. So, overall if you work out the error probability, that will be bounded by n cube by n. So, your error probability is going to be strictly less than n cube by n. Okay. And if you choose capital N to be greater than, let us say, n cube, then you know that the error probability is very small. And so, if the, and of course, if the adversary had given the correct value each time, then we will verify all the steps, we will see that all the consistency criterion are really met with, and therefore that causes no problem. If the adversary lies even once about the permanent of a submatrix, we can force him to propagate his lie, and in the end he will get caught. The probability that he does not get caught is bounded by n cube over n. Okay, so, that brings us to the end of the LFKN protocol.